There's a battery that does not need charging. It does not need sunlight. It does not need a wall outlet or a generator or a single drop of lithium. It needs one thing: seawater. You take a strip of magnesium, a plate of copper or silver chloride, and you dip them into a cup of salt water. And the moment that magnesium touches the ocean, electrons begin to flow. Not a trickle. A real, measurable, usable current. Enough to light an LED, enough to charge a phone. Enough, if you scale it, to drive a torpedo through the Atlantic at 45 knots. And this is not some new breakthrough. This battery was invented in 1940 by Bell Laboratories, 86 years ago. It powered Allied torpedoes in World War II. It powered sonobuoys dropped by Navy aircraft into the Pacific. It powered emergency beacons on life jackets inside every commercial airplane. And it has been doing this quietly inside classified military budgets ever since. The question is not whether it works. The United States Navy has used it in 14 different navies across 5 continents. The question is why you have never heard of it, and why right now you're paying $16,000 for a lithium wall battery that degrades, overheats, and contains minerals dug out of the ground by children in the Congo. Let me start at the beginning. In 1943, the Mark 44 torpedo needed a battery that could sit inside a weapons bay for years and still deliver full power the instant it hit the water. Lithium was not an option. Lead acid would corrode. Nickel-cadmium was too heavy. So engineers at Bell Labs built something radically simple. They took a magnesium alloy anode and a silver chloride cathode and separated them with a porous spacer. No electrolyte was added. The battery was assembled completely dry. It weighed almost nothing. It could sit on a shelf for 5 years without losing a single % of its charge. 0 self-discharge, 0 degradation. And the moment the torpedo hit the ocean and seawater rushed through a scoop in the hull, the battery came alive. Ions moved through the salt water. Electrons flowed from the magnesium to the silver chloride. And 146 cells stacked in series delivered 160 volts and 32 kilowatts of power for 6 straight minutes. That is enough energy to push a 500-pound weapon through the ocean at combat speed from a battery that was dead 30 seconds earlier. Let that sink in. 32 kilowatts from salt water. The company that perfected the modern version of this battery is SAFT, a French defense contractor based in Poitiers. Their V616 battery is the sole qualified power source for the A244 torpedo, which has been used by 14 navies around the world. The spec sheet is public. You can read it yourself. Nominal voltage, 160 volts. Peak voltage, 190. Cutoff voltage, 140. Operating temperature range, 0 to 30 degrees Celsius. Weight, 34 kilograms dry. Storage life, 5 years minimum with 0 maintenance. And the electrolyte cost is exactly 0 because the electrolyte is the ocean itself. Now, let us talk about what magnesium actually is, because this is where the story gets uncomfortable for the lithium industry. Magnesium is the 8th most abundant element in the Earth's crust. It makes up 2.9% of everything under your feet. By contrast, lithium is the 33rd most abundant element, at roughly 20 parts per million. That means there's over 1,000 times more magnesium in the ground than lithium. And it is not just in the ground. Seawater itself contains 1.35 grams of dissolved magnesium per liter. The ocean is literally saturated with the stuff. The American Chemical Society documented that 1 ton of magnesium can be extracted directly from seawater using a basic chemical process involving oyster shells and hydrochloric acid. That process has been running industrially since the 1940s. The Dow Chemical Plant in Freeport, Texas, extracted magnesium from the Gulf of Mexico for decades, and the current global price of magnesium metal sits at roughly $2.50 per kilogram. Compare that to lithium carbonate, which trades at around $15 to $20 per kilogram even in a down market, and cobalt, which runs $40 to $50 per kilogram and comes primarily from artisanal mines in the Democratic Republic of Congo, where children as young as 6 dig with their bare hands in tunnels that collapse without warning. 70% of the world's cobalt comes from the Congo, and every single lithium-ion battery you have ever owned contains cobalt. Your phone, your laptop, your Tesla Powerwall, everyone. Magnesium requires none of this. It is everywhere. It is cheap, it is non-toxic, and it does not explode. This is an important point. Lithium has an ignition temperature of 355 degrees Fahrenheit. Once a lithium battery enters thermal runaway, it produces its own oxygen. You cannot smother it. You cannot drown it. Fire departments across the country have documented cases where lithium battery fires burned for days. The National Institute of Standards and Technology published Technical Note 2365, specifically documenting the risk of lithium-ion battery fires in consumer products. Magnesium, by contrast, has an ignition temperature of 883 degrees Fahrenheit, more than double. And a magnesium seawater battery does not contain a volatile organic electrolyte. Its electrolyte is water. Try setting water on fire. So we have a battery chemistry that is cheaper, safer, more abundant, non-toxic, stores for decades without degradation, and activates instantly with a resource that covers 71% of the planet. And it was proven in combat 80 years ago. Now here is where it gets real. In 2009, a Japanese company called Aqua Power System Japan launched the world's first commercial water-activated magnesium battery. It was a standard AA size, 1.5 volts, and it was activated by adding a few drops of water. They branded it No Popo, and they sold over 8 million units across Japan and Asia. 8 million. Not a lab prototype, not a Kickstarter. A real product, in real stores, purchased by real people who simply added water and got power. The company later acquired exclusive rights to magnesium air fuel cell technology and began developing higher power versions for emergency lighting, portable radios, and disaster relief kits. Japan, after all, sits on the Pacific Ring of Fire. Earthquakes destroy infrastructure. The grid goes down. Gasoline pumps stop working. Solar panels get buried under debris, but the ocean is still there. And a magnesium battery that has been sitting in a closet for 5 years will work the moment you add water. Then, in 2020, a Colombian renewable energy startup called Edina took this a step further. They built a device called Waterlight. It is a portable lantern shaped like a cylinder with a wooden case carved by indigenous Wayuu artisans on the northern tip of South America. You fill it with 500 milliliters of seawater, and it produces light, not for an hour, not for a day, for 45 days from a single fill. Inside the device, magnesium and copper plates react with the salt water through ionization, generating a continuous electrical current. Edina patented a method of sustaining this reaction far longer than any previous technology. Over its lifetime, one Waterlight unit produces approximately 5,600 hours of energy. That is 2 to 3 years of regular use. And it has a USB port. You can charge your phone from it. Time magazine named it one of the 200 best inventions of 2022. Wonderman Thompson designed the product rollout specifically for the Wayuu people, an indigenous community that has been abandoned by the Colombian government and lives without electricity on a desert peninsula surrounded on 3 sides by the Caribbean Sea. The irony is staggering. They live surrounded by an ocean that contains an infinite supply of battery electrolyte. And until Waterlight, nobody thought to give them a device that could use it. But Waterlight is just a lamp. What about real power? What about running a house? This is where the science gets exciting and the industry gets nervous. A magnesium air battery, where the cathode reaction uses dissolved oxygen from the air or water instead of a metal salt, has a theoretical energy density of 6,800 watt-hours per kilogram. That number comes from the Eureka Patent Analysis Platform and has been confirmed by a 2023 review in the MDPI journal Processes. For context, a Tesla Powerwall 2 uses lithium, nickel, manganese, cobalt oxide cells with an energy density of roughly 260 watt-hours per kilogram. Magnesium air is theoretically 26 times more energy dense than what is currently bolted to the side of your house. Even in practical, real-world configurations, magnesium hydrogen peroxide semi-fuel cells, developed for the Norwegian Hugin 3000 autonomous underwater vehicle, achieved 260 to 400 watt-hours per kilogram. That is already on par with, or exceeding lithium-ion, at a fraction of the material cost, with no fire risk, and with seawater as the electrolyte. The Norwegian Defense Research Establishment used aluminum hydrogen peroxide seawater batteries to extend AUV endurance from 4 to 10 hours, with zinc-silver batteries all the way up to 30 to 60 hours. These are real deployments in real ocean environments at real depths, published by military research institutions. And the Chinese Academy of Military Science published a comprehensive 2023 review in the journal Sustainability, documenting every major seawater battery deployment from the 1940s to the present. Here are the facts from that paper. In 1996, a seawater battery powered the automatic control system of a submarine oil well at a depth of 180 meters in the Ionian Sea, running stably for years. In 2000, Japan installed a seawater battery system at 5,500 meters depth in the northeastern Pacific Ocean. 4 batteries connected in parallel provided an average power of 13 watts continuously for 5 years. Not 5 hours, 5 years, at the bottom of the ocean. And the French Navy and the Norwegian FFI jointly developed the Clipper autonomous underwater vehicle. It ran on 6 dissolved oxygen seawater batteries with 234 magnesium rods each. Total battery power was 678 watts. It operated for 2 weeks under Arctic conditions at 600 meters depth. The researchers specifically noted that seawater batteries are extremely safe because they do not require a pressure-resistant container. The ocean itself is the battery. So why can you not buy one? Here's the truth that nobody in the battery industry wants to say out loud. A battery that uses seawater as its electrolyte and magnesium as its anode generates almost zero recurring revenue. You cannot sell someone a monthly subscription to the ocean. You cannot license the salt content of the Pacific. You cannot build a proprietary charging network when the charging station is every coastline on Earth. Lithium-ion batteries, by contrast, generate revenue at every stage. Mining companies sell the lithium. Refiners sell the processed cathode materials. Manufacturers sell the cells. Installers sell the battery packs. Software companies sell the battery management systems. And every 7 to 10 years, the whole thing degrades below 80% capacity and you buy a new one. It is a $16,000 purchase that becomes a $32,000 lifetime cost. And the entire supply chain depends on scarcity. Lithium is scarce. Cobalt is scarce. Nickel is scarce. The factories that process them are concentrated in China. The mines that produce them are concentrated in Australia, Chile, and the Congo. Every link in that chain is controlled by someone who profits from the fact that you have no alternative. Magnesium breaks that chain. It is everywhere. It is cheap. It does not degrade on the shelf. And its electrolyte falls from the sky as rain and covers 71% of the planet as ocean. Now, I need to be honest about the limitations, because this channel does not do hype without reality. First, magnesium seawater batteries as they exist today in military and emergency applications are primary batteries. That means they are single use. You activate them, they run, and when the magnesium anode is consumed, they are done. The magnesium corrodes during discharge. A 2025 study in the Journal of Alloys and Compounds documented that the hydrogen evolution reaction on the magnesium surface causes significant self-corrosion, creating a passivation layer of magnesium hydroxide that blocks further reaction. This is the fundamental challenge. In an aqueous electrolyte, magnesium wants to corrode even when it is not delivering current. The anode literally dissolves. Researchers have made progress by alloying magnesium with calcium, lithium, aluminum, lead, indium, and rare earth elements to slow this corrosion and improve efficiency. A magnesium-calcium alloy achieved a stable cell voltage of 1.6 volts at 1.5 milliamps per square centimeter and an energy density of over 1,400 watt-hours per kilogram. But none of these alloys completely solve the problem. The self-corrosion continues. Second, the power density of dissolved oxygen seawater batteries is low. Because oxygen concentration in seawater is limited, these batteries are best suited for long-duration, low-power applications. 13 watts sustained for 5 years is extraordinary for an ocean floor sensor. It is not going to run your air conditioner. Third, the high-power forced flow torpedo batteries deliver massive power, but only for minutes. The V616 runs for 6 minutes. You are not powering a house for 6 minutes and calling it a solution. Fourth, rechargeable seawater batteries are being developed. In 2014, Korean researchers proposed and patented a rechargeable seawater battery that uses a sodium-ion conductive solid electrolyte to separate the anode from the seawater cathode. The theoretical cell voltage is 3.48 volts. Early prototypes have shown reversible capacity over 80 cycles, but these are still in the lab. Commercial versions do not exist yet. So what can you actually build? Here is a practical design that uses proven available materials. You take a magnesium alloy rod, available online for $2 to $5. You take a copper plate or a carbon rod, available for $1 to $3. You place them in a container and fill it with seawater or make your own electrolyte by dissolving 35 grams of table salt in 1 liter of water. Each cell produces approximately 0.9 to 1.6 volts, depending on your cathode material. Copper gives you roughly 1.0 to 1.2 volts. Silver chloride gives you 1.5 to 1.6 volts. Carbon with dissolved oxygen gives you about 1.0 volt. You wire 4 cells in series, and you get 4 to 6 volts, enough to power LED lights, a small radio, a phone charger through a boost converter, or any low-power device. The total material cost is under $10. The electrolyte cost is $0 if you live near the ocean. The magnesium rods will need to be replaced periodically as they corrode, perhaps every few weeks of continuous use, at a cost of a few dollars each. This is not free energy. It is extremely cheap energy with zero infrastructure requirement. For comparison, a single 100-watt solar panel costs $80 to $150, requires sunlight, requires a charge controller, requires a battery to store energy for nighttime use, and that battery is usually lithium-ion, which adds another $200 to $500. Total system cost for a basic off-grid solar setup is $300 to $600, and it only works when the sun is shining. A magnesium seawater battery setup costs under $10 and works 24 hours a day, rain or shine, day or night, as long as you have salt water. That is not a marginal improvement. That is a different category of technology. The 840 million people on this planet who live without electricity are not waiting for Tesla to build a gigafactory in their village. They are waiting for something that costs less than a meal, uses materials that are already around them, and works the moment they need it. The magnesium seawater battery is that thing. It has been that thing since 1943. And the only reason it is not in every coastal village, every fishing boat, every disaster relief kit, And every off-grid cabin on Earth is because the people who sell you lithium batteries would go bankrupt if you knew about it. Share this with someone who lives near the ocean. Share this with someone who pays an electric bill. Share this with someone who was told that lithium is the only way. It is not. It never was. The ocean has been holding the answer for 86 years. All you had to do was add water.